Hi, welcome everyone to your energy, work, and power lecture. We'll start off, as always, with a bit of a review. So we'll go back and, for this first question, just look at a little bit of a conceptual um, approach to the impulse momentum equation and concept that we covered last day. And here we're going to try to apply it to the sport of football. So we have a small in mass and size or stature, a small high school football player who's wanting to be more formidable on the field, in particular with their tackles. Using what you know, the knowledge that you have, apply the impulse momentum equation and concept to this and try to give them some guidance on what they can do to improve their tackling. Again, I'll just carry through in a moment, but take a moment, pause, consider a few aspects, what makes sense, and then how do you use the equation to do that, okay? So go ahead and pause. But continuing on, if we look at the equation here, we can see that there's a few avenues potentially the player could leverage to essentially increase the force experienced by this impulse momentum equation, right? So one of the first ones, if we take the size of the player and we say, you know what, yeah, maybe we can get them to hit the gym, get a bit more muscle mass, and that should help increase the total force if we increase mass, because force is proportional to it. Potentially, that's one avenue to go. A second side effect maybe that might have, depending on, again, the type of mass, whether it's muscle versus, say, body fat, is the increase of the final velocity that the player is able to hit. So maybe we suggest the player does a bit more speed work, ends up building their physiology to be able to move quicker and increase their velocity with or without the mass increase. That would still increase the total force that they could apply. And then let's assume they've really done as much training as they could. They've increased their mass in the gym. They've done all the speed work, and based off of their mass, they get moving about as fast as they can. Just looking at this side of the equation, again, assuming this is fixed, to increase force, we can get them to decrease the amount of time that they apply the hit to, right? So that concept of impulse where a short amount of time with the same amount of force, so the same mass and velocity, just applied very abruptly, will lead to a bigger sum of force experienced by the tackle. Okay. So again, a few different avenues there. Hopefully you managed to get one, or hearing the explanation made sense for some or all of them. Okay. Next up, we'll move on to an equation, and again, applying the hockey shot. Applying the impulse momentum equation to a hockey shot, and being able to utilize that to figure out a few things here. So if we look at the first question, it says a hockey player is practicing their wrist shots, and they start out reaching a final velocity of 40 meters per second, and they do so over 0.025 seconds of contact with the puck as they apply some force. The puck, as we all know off by hand, is 160 grams, and it's stationary to start with because they're just practicing, right? It's not moving in gameplay. What is the force of the puck? Okay. So yeah, let's figure this out. And again, our typical steps: what do we know? What do we not know? We have a good idea already that we're using our impulse momentum equation. So let's take a look here. We know that, the final velocity is 40 meters per second. And if we recall, we know the initial was 0 because it's stationary. We are also given the mass of the puck that says 160 grams. But wait a second, grams. That's not our SI unit, so we have to convert. So we have 0.16 kilograms. Then we see that they also give us time. So we have time in this question, and that is 0.025 seconds, okay? So with this, we can plug that into our equation, which is force times time equals mass times velocity final minus velocity initial, or delta V. And even to set ourselves up, we kind of know what we have here. We're looking for force, so we know our one unknown variable. So all we need to do is move time over to the other side. So before we even start plugging in equations, we can, or variables, we can simply move that over there. And now we can just plug and play. So what do we got here? Well, our mass was 0.16 kilograms times our change in velocity, which is 40 meters per second. I gotta stick with writing units or not. There we go. Let's just go with not for now. And of course, our time was stated to be 0.025 seconds. So once we calculate that all out, we find that our force is equal to 256 newtons. Okay, great. So now we have that force there. We're just going to roll that up. So that was A. When we look at B, we see that the hockey player has, by the end of the practice, managed to increase their range of motion, so they have a greater drawback on their wrist shot, and that allows them to keep more contact with the puck over a longer period of time. Okay. They also are able to, during this, increase the force that they've applied to this puck by 14 newtons. So that's great, right? More force being applied over a greater amount of time. So with the same weight mass puck, because that doesn't really change, what is the final velocity? How fast is the shot now? We knew it was 40 meters per second prior. Well, what is it now? So let's use the same impulse momentum question and apply the new data that we got. All right, so let's see. Let's go like this. We'll go our force times time equals mass delta V. And again, even though we have we're trying to find the final velocity, we know the initial velocity is 0 again, okay? So VF, and we can still write it as delta V. It's the same expression, right? So final velocity, initial is 0. So when we go final minus initial velocity of 0, it just gives us whatever our answer is. We know our mass is still 0.16 kg. We now know that our force was the same as before. Wow, okay. 256 newtons plus now our new and improved 14 newtons. So once we calculate that out, that gives us 270. Okay, so that's our new force. And time, also a little new and improved. We got 0.5 seconds, okay? So again, we can rewrite this initial equation just to help us figure out what we're looking for. And we know we want to find that as our final variable, which means we move this over to that side. So we divide by both sides. So that equals our delta V, which we can also just call V final. That's what we're looking for. Okay, and for convention, we'll flip that around and start plugging in numbers. So our final force was 270. Our time was 0.05. And our mass, 0.16. So when we plug that in, what we have is 84.3 74.75, or we can just round up to say 84.4 meters per second. Okay. Great, so significantly faster than the shot from part A, which was 40 meters per second, right? Twice is the velocity, so that's great. Just by increasing time and force. Okay. So that's a bit of a review again for momentum impulse. You've had a lab on that now too, and so hopefully that's feeling familiar for you. Okay. So we'll take a quick moment here, and well, hopefully this plays and works. Hopefully it doesn't mess up the audio too much, but we'll just take a look at some of the more fun ways that this concept of energy and work all comes together. So we see here, this is one of the most thrilling parts of cycling, and you'll note that these cyclists are getting to speeds of about 66. Eventually they get on to about 75 kilometers an hour. And on a gradient of a hill that's maybe like 7%, 8%, it's pretty achievable. And it's just an absolute blast. Just hammer down the hill, get nice and aero, so decrease air drag or forces applied in the opposite direction to you want to go, and utilize our topics of today. So utilize things such as stored energy and power applied to the bike, and a few principles that way. Okay, and we'll see again by the end of this lecture, how is this achievable? How are these cyclists at a very low work rate relative to what they probably typically put out? How are they able to hit speeds of 72 kilometers an hour pretty easily? Okay, and so let's dive into that. And so today, energy, work, power, and we'll end up applying energy in particular to human physiology and how we get our energy. But before we get to that, let's explore the idea of energy generally speaking. Okay, so here we have energy as defined as the capacity to do work. Okay, it cannot be created nor destroyed, just merely transferred. So what does that mean? Well, it means we have this constant amount of energy in the universe, and that's fixed. Okay, and this is one of the best tested ideas and theories in science to date. We know that anytime that a force is acting upon an object or body, that it's transferring or transforming energy in some way, shape, or form. Okay. But when we look at this definition of energy, it's the capacity to do work. Well, we need to define what work is, right? What the heck is that? Let's understand that concept a bit better in and of itself, okay? Okay, work. What is work? Well, work is done on a system by a constant force. It is the product of the component of the force and the direction of the motion multiplied by the distance through which the force acts. Okay, and again, we know that forces and different vectors can happen on angles. So to account for this, when we have our equation, we write cosine theta. Okay, so ultimately, what are we looking at? Well, we're looking at the force times distance based off of the component of work that's applying one-dimensionally to whatever object is being worked on. Okay, let's try to say that again in maybe a slightly different way. It's a bit more clear. So work is directly proportional to the force that's being applied, and we can see that here again in this work equation. And the displacement relative to the angle, so that's again displacement or distance, if it's linear, times the cosine of the angle. Okay. So if it's more than one axis, typically we'd have to figure out the forces and the work on either axis. Typically we'll be dealing with just a single direction here. And when work is done, just as a reminder, energy is being transferred. Okay. When we look at the SI units now, you could call it Newton meters. And if we look at the equation again, force times distance, well, we have newtons, so that's force times our distance, which would be meters. That's SI units. But a lot of the times we'll typically look at 1 joule. Okay. So how much energy is 1 joule, and how much work does that kind of relate to? Well, if we think about a joule, it'd be the amount of energy that we need to lift a small apple, so like 100 grams, about 1 meter, so like 1 ruler stick, or like a meter stick from classroom, right? Ruler, so larger one. Okay, so 1 joule is an apple, 1 meter. Okay. All right, well, let's apply this question. We'll do some calculating, see how conceptually we understand it, see how we can calculate it out. I think for this case, again, we'll give you, go ahead and pause if you need to, take a chance to, or an opportunity to go through and try to work through it on your own, and then I'll go through it now momentarily, okay? Great. So let's go through the question together, okay? So for question A, we have Joe here standing, holding a briefcase. We see that some force is being applied to hold the briefcase up against gravity. What sort of work is done? Okay, well, if we take a look at the equation, we see that work is a force, which we have, times distance times the cosine of the angle. Well, cosine of the angle is really, we can kind of negate that in this case. It's purely on one axis vertical, so we can negate that. But the direction or the distance that is changed, or in this case not changed, means that d equals 0. If the displacement or distance equals 0, there's no work that's done, okay? But could we agree that there's some sort of force being applied to the briefcase? Yeah, for sure. You have to hold up the briefcase somehow, right? Okay, so again, you need both work, or so you need both a force and distance that force is applied over in order to have any work done. Okay, so a good example here to try to reinforce that idea is even though we might say in common language that someone doing a plank is working really hard, they're actually not, right? They might be expending muscular energy to stay up, but ultimately they are not doing any work because the distance that they are covering is 0, or their displacement is 0, right? Okay, let's move on to part B. So part B, we have some distance being covered and a force being applied. So we know already work's being done. Great. Joe's moving, is mowing the lawn and is pushing the lawnmower with 75 newtons of force on the handle. The handle, however, is downward at 35 degrees to the horizontal, and Joe moves across the lawn 25 meters. How much work is done? Okay, again, we see a force, we see a distance. So, sure enough, we can turn to our work equals force times distance times cos theta. And again, just as a reminder, you can set yourself up like that. What are our knowns? Well, we know force, is 75 newtons. We know the distance is 25 meters, and we know theta is equal to 35, right? Great, so let's plug and play. Here we are. We got 75 times 25 times the cosine of 35 degrees. And what do we do when we crunch those numbers? Well, we get 1,535.9. And what unit? Drum roll. Joules. That's right. Big J. Okay? Good. So we see, again, work. And you might have come across this concept before as force times distance. And now we can calculate, and same if it's applied on an angle, right? Okay, so now that we understand work and the fact that energy is just the capacity to do work, and work is a force over a distance, so energy, in another way of saying it, is the capacity to, or is when a force is applied over a distance. The capacity to have a force over a distance, okay? Now, keeping that in mind, when we think about the whole universe, we know energy is conserved, right? That was the first point we were talking about when we brought up energy. Now, it's also transferred or transformed, okay? So what does that mean? What does that look like? Well, we have different types of energy. And all energy is the capacity to do work, apply a force over a distance in some way. So we have a number of different ones, a lot of which you've heard. And I'm not the biggest fan of some of this infographic, but I use it because it looked good. And some of the main ones here that we'll be looking at is really helpful. Okay, so mechanical energy is the physical energy that we have, a capacity to do work. We have thermal, we have gravitational, and then a lot of those kind of feed into kinetic and potential energy as types, okay? And there's chemical energy as well, okay? Well, we have some examples here, but let's even get some better examples. So if we look at types of conversion of energy, one of the most applicable to us in sports sciences is chemical, okay? Chemical to, eventually kinetic energy. That's mainly what we're interested in kinesiology and sports science. So we see here, someone's eating an apple. Well, that has chemical stored energy. And when we dehydrate, which is essentially a type of chemical reaction that removes water out of compounds, what we end up getting is water, glucose, and water, CO2, and stored energy in another molecule that we then use for energy later in the form of ATP. You might have heard of that. Okay, that's our cellular energy currency, right? Is ATP. Okay, so we kind of take chemical energy, change it around, it becomes different stored chemical energy, which then our muscles can use to perform work, right? Again, energy is just the capacity to do work. When we talk about renewable sources of energy, very, very crucial to our energy demands moving forward and keeping our planet healthy. We see different types of transformation of energy. So solar is radiation energy from the sun, light through electromagnetic radiation that we can then store, turn into electrical energy. And a lot of what solar power actually does is take that radiation energy, turns it into photovoltaic energy, which we then convert actually into heat that we store in things like molten salt piping. And then we take that heat energy and use it to make steam to drive a turbine, which is mechanical energy, which we then turn back into electrical energy to send to our homes to power things. Okay, so there's actually purely just in the way that we have developed solar technology, to create energy for homes requires multiple transformations of energy. Okay. All right, and here is a brilliant example of taking potential energy at the top of a hill and turning it into kinetic. And this is through the means of mechanical energy, okay, under the umbrella of that term. And that is largely where our focus is going to be for this class, okay? But first, let's take a look at how we can take potential energy, turn it or transfer it into kinetic energy and back again, okay? Here we go.
Take a look. These are big, heavy rubber bungee cords. And this is a sandbag. It's a heavy weight. So the weight holds the center of the bungee cord still. When the barrel rolls, they twist, storing energy in the rubber. Watch. When I give it a kick, it's storing energy. See, the weight holds the middle of the bungee cords tight, so they wind up.
The energy from the kick is stored in the bungee cord.
As it rolls back, we get that energy back as kinetic energy, see?
Oh, ah, ah, ah,
Brilliant. And you thought Family Guy was clever. They just stole it from Bill Nye. All right. So what did we see happen there? So we had this bin rolling, and it seemed to be picking up some velocity or some speed. So it had more, and it had this kinetic energy. It was moving. So things that are moving have this kinetic energy. And then all of a sudden it stopped and started coming back. Well, if we know energy of a system must be maintained, when we look at a system with mechanical energy, we can see that as something starts moving more and more, like this blue line, is picking up kinetic energy. And it's losing its potential energy, but the mechanical energy will stay the same the whole time. Like that doesn't change, right? So what is potential energy? Well, in the case of the rubber bands, our kinetic energy actually started high. So Bill Nye gave the barrel a kick, had high kinetic energy, and it actually started getting less and less as the rubber bands got more and more potential energy, to the point where the barrel had no more kinetic energy, so it stopped. Kinetic is moving, right? But then the band started applying some of the potential energy and transferred it again into kinetic. So the kinetic energy started picking up again. The potential energy in the bands were getting drained, I guess you could say, and until the point where it hit Bill's shins, right? So that's I find that this is a good graphical representation of that kind of trade-off between the two. Okay, as we'll come to see, things from a height have potential energy. So we could say when someone drops an object, it has maximum potential energy and minimal kinetic energy at the time. When they let go, it spikes because all that potential energy gets transferred into kinetic energy until it hits the ground where it has maximal kinetic energy and minimal potential energy. Okay? Let's see that played out one more time in a slightly different way. I love this. This is Neil deGrasse Tyson. If you don't know who this is, he's brilliant. You know, such an entertaining and fun scientist, physicist in particular. And here he's just demonstrating that you can safely and knowingly let a very heavy pendulum swing, and that it will return exactly where it was, because again, the total mechanical energy, so this green bar, is going to be the same the whole time. As it moves away, picks up kinetic energy, translates into potential, where that potential energy is transferred back into kinetic, right? And just trades off between the two again, despite the total mechanical energy being the same. Right? You see the sledder, as they come up the hill, they gain more and more potential energy, less and less kinetic energy. Okay. But why is that? You might be questioning this already. This has come up 2 or 3 times, and I've been planning to see it as best I can. Why is it that as things have height or elevation or go up a hill, they have more potential energy, right? Remember the cyclists, as they're flying down the hill, they had a lot of potential energy they're converting into kinetic. Why? What exactly are the variables that are important for kinetic and potential energy? Well, let this answer your questions. Kinetic energy is half mass times the velocity squared of an object. Okay? Potential energy is the mass of the object times gravity times the height at which it's at. So when we're speaking about mechanical energy specifically, and how much kinetic and potential energy that object holds, these are the variables that define it, okay? So if we can just think, all right, one of the most important variables here, velocity. The faster something's moving, the more kinetic energy it's going to have, okay? For potential energy, and you can say potential gravitational energy, but we're in the realm of mechanical energy here. We know that it's mass times gravity times the height at which that object is its potential energy. So what does that mean? Something really, really high has a lot of stored potential mechanical energy. Okay. What are things that we know about this? Skiing, snowboarding, sledding events, rivers that start up high and flow downward have a lot of potential energy. Things that you roll down from the top of a stairs or set downstairs like a slinky, right? These have potential energy that gets converted into kinetic energy as they get lower and lower down the hills. Okay, here we have some street lugers. And something to keep in mind is you can set up an equation here like at the bottom. So it says in a frictionless system, and it's true because we don't have any non-conservative forces being applied to this system. We can see that it's the starting total mechanical energy of a system, so on the left side here, must equal that same system at the end of whatever's occurred. Okay, so we can say on the left here is at the top of a hill, on the right is at the bottom of a hill. Or we can flip that around. It doesn't matter how we set it up. It's just the system, and again, this is the conservation of energy, is the same on any 2 points in time. They have to add up to equal the total mechanical energy. Okay. So, how can we apply this in a fun way? Well, let's take a look here. Let's take a sport like luge, okay? And we're going to see how it's lugers' initial total mechanical energy at the start of a luge can help us figure out something kind of cool for the end of their run, okay? So let's take a little look-see. A luger starts at the top of a 1-mile track. The finish line is 120 meters lower than the start line in elevation. The average weight of a luger is 70 kilos. So how fast is this luger going at the finish line? Okay. And it's just funny saying luger because, well, yeah, anyway. But let's take a look at this, okay? Because these are real numbers. So on average, a track is about a mile. It's about 120 meters elevation change between the start and the end of this mile. There's set percent gradients that have to be abided by for artificial tracks like this. And the average weight, I just kind of pulled, I think in reality, it's probably a little heavier because the heavier you are, the more kinetic or potential energy you can have, right? Okay, but again, let's take a look at this. So what do we know? It gives us some information here. So we finish 120 meters lower than we started at. So we can say that at our start line, because we know we're starting with the most potential energy at the top of the hill, and we know potential energy is mass times gravity times height, we can say that our height at the start line is equal to 120 meters. So that means that our height at the final, we'll say, is at our 0 meter mark. Okay. Our average weight for our luge, so our mass, both at the start and the mass final, because they're not changing weight as they're descending the track, is 70 kilos. And last but not least, we can look at our velocities. So our initial velocity at the start is 0 meters per second, as per normal luge protocol. But at the final, well, that's what we want to find out. Okay, so let's set up this equation and we'll see what we can do and solve and figure out. With our kinetic energy, let's even go up here. So our kinetic energy at the start plus our potential energy at the start is equal to the kinetic energy at the finish line plus the potential energy at the finish line, okay? So that's all we're filling in right now. Our potential energy is, again, mass times gravity times height, and that is equal to, same over here, which is 1/2 mv squared plus mgh. Okay, well, right away with this, we see some zeros floating around. Okay, so let's use that and fill them in. So we got our finishing height, which is 0. So if this is zeroed out, that means this whole term is zeroed out. Okay, so that's our height. Velocity at the start, that's zeroed out, so that whole term is zeroed out. So let's rewrite this. So our mass times gravity times height is purely equal to the half mass velocity squared at the end of the run. Okay, so this is already starting to look a little less cumbersome than maybe that first equation, right? So again, let's just keep plugging in numbers and going from there. I think I'm going to switch to the same color for everything now. Okay, so let's take a look here. The mass, we know at both points is 70 kilo. Gravity is our gravitational constant. Now keep in mind, when you're calculating potential energy, we don't put in the directionality, just the magnitude here. And our height is 120, and that is going to equal, let's keep different colors. Okay, that second component here, which is going to be half times our mass, which is 70 kilo, times our velocity squared. Okay, and of course we want to get that away so we can isolate our velocity. So we can rewrite this whole thing out one more time, and we'll just switch the sides for convention to get velocity on the left here. So velocity equals, and again we're just dividing both sides by this to move it over, so it equals 70 kg, sorry, that's still squared, times our gravitational constant, times 120 meters in height, so this is our potential, divided by half of our mass. Good. And again, for those that are more comfortable, you could square root the other side right now, but just to make sure we have more steps, again, break everything down into little steps whenever you're calculating things out. We see that this equals 2,354.4, but we're not quite done. We can't forget that. So now I'm going to square root that. And what we see in the end is we have 48.5 meters per second. Okay, that's our final velocity. Now, if we just ponder for a second, do a little check. Okay, well, how fast is about 48.5 meters in kilometers per hour? That's about 175 kilometers per hour. Okay, so that's really, really fast. Now the world record is, I think I saw it was like 150 kilometers per hour. Still really, really fast. But one question that you can kind of ask yourself to make sure that you understand the concept of this is, why are those different? So again, think back to how we're setting up this question. We're making it an idealized scenario, right? So in a perfect scenario, no friction. Okay, but in reality, we have frictional forces both, somewhat between the blades of the luge or the sled and the ice, but also you have drag and air resistance, right? So we do have forces that detract from this hypothetical speed that we should have, that we initially get from our potential energy. Okay, but there we go. We were able to figure out, based off of some knowledge about the track and our sledder, how fast they got going by the end. It's pretty cool. Great. So once we have the conservation of energy, kinetic energy, and potential energy understood, we can move forward into a slightly different topic, but related to work and energy, is power. Okay, so again, this is another term. This whole lecture really has a lot of this, where a lot of terms that we use day to day have very specific and sometimes different meanings than what's intended. Okay, so when we're talking about power specifically, we're talking about the rate at which work is performed. And remember, work is a force times a distance, right? Or a distance or displacement in which force is applied. So this is the rate, how quick or how much of work can be done in a certain amount of time for a certain object and or system. Okay, and power is measured in watts. So if you think about this, this kind of makes sense. If you look at a light bulb, light bulbs have wattages, right? So the amount of work that they can perform, electrical, over a certain amount of time, and they can all handle or produce a certain amount of watts based off of that. Okay, but let's take a look at that power, what that looks like when we're applying it to people and human movement. So in this practice activity, again, pause, go ahead, try to calculate through. But we're looking at someone who is powerlifting, okay? So they're gonna lift this barbell up over their head from the ground, and we know the weight of the barbell. So it's 110 kilos. So when we multiply it by gravity and we get our newtons for that, that's about 1,000 newtons. And this person's gonna lift it up overhead, so 1.5 meters. And in one scenario, she takes 1.2 seconds to do this. In another scenario, she pauses partway up and then pushes overhead, okay? So it's a bit of a longer, slower, drawn-out scenario. So let's figure out in either one of these scenarios what the power demonstrated was, okay? So pause, go ahead and do that now, and I'll continue through with the calculation and explanation, okay? Okay, so we're taking a look at this. Here we have our person, and I've bolded a lot of the information for us. So what do we know? Well, we know that we were giving a force in newtons, which is derived from the weight of the barbell. We have the height, or I guess in this case we could also call it the distance or displacement traveled by the barbell. And then we also have time 1 and time 2. Okay, time 1 is 1.2 seconds, and time 2 is 4.5 seconds, okay? So when we're setting up our equation, we know it's asking for power, and we want to provide that, so we go power equals work over time. But we see in the question here, there's nothing given to us in joules. So what do? Well, what we can do, we haven't done a lot of this in class per se, but we can look at work and we can say work is also equal to force times distance, cosine theta, but there's no angles to account for here. So what we can do is we can take this term and just replace that one. So we can rewrite power to equal a force times distance over time. Okay, it's saying the exact same stuff. This is equal to that equation, okay? So from here, do we have all our variables? Yeah, we got force, we got distance, and we got times. Great. So what we can do is we can just plug and play. We have power equals our force, 1 newtons, times our displacement or our distance, 1.5 meters over. In this first scenario is 1.2 seconds. And I can even just bounce ahead a bit and say, you know what? I'm going to set up my second equation while I remember these numbers, because the height of the person and what they can reach and the barbell doesn't change. The only thing that changes is the seconds, okay? And then from there, of course, I can calculate my final numbers. And for this first equation, I have 1,348. And for the second one, I have 3,500 and, oopsies. We have 300, 559.7. Okay, and I made a mistake in trying to be quick. Again, a note to take your time when you're doing these. The unit is watts, okay? Watts, and it's spelled like watts, okay? So we can see that scenario 1 with the shorter amount of time indicates a much greater amount of power, so the work over time, relative to the second time frame, okay? So hopefully you got something like that. Great. So that's fun, checking out those variables and calculating some of those things. But let's look a little bit closer at human physiology, how it might relate to exercise physiology, and the relation to energy. So when we're looking at energy for the human body, we're really talking about metabolism. So our bodies use energy. We know this, we say it in common language. But that definition before, if you remember, was energy is the capacity to do work, okay? So how do we do work? How does our bodies allow us to do work? And really what that is transforming energy from chemical bonds to other chemical bonds to mechanical work, right? Helps us move around, helps our cells stay alive. Our cells actually have components that move as well. So, yeah. But I think the biggest difference between when we're talking about mechanical energy and energy just at the greater realm of the world and how our bodies use energy is more in our language and our terms when we refer to calories. So calories are the amount of heat, by definition, or the amount of heat that it takes to raise 1 gram of water by 1 degree centigrade in temperature. Okay, so essentially if you picture like a small amount of water and the amount of energy that you need to put into there, so heat energy, to make it raise its temperature by 1 degree Celsius. Okay, and I should note that there's big C and little c calories. The difference is big C calorie is a kilogram of water versus a gram. So it's 1,000 times larger, okay? So when we look at 1 kilocalorie, that would be related to 1 big C because it's a kilo, okay? But if we look at 1 kilocalorie, it has 4,000, roughly 4,200 joules, roughly, okay, of energy. So that's how we can relate the two. When we talk about our food and we see calories on the side of the box, we really can convert that to actual joules that we would use to calculate work done by any other object or system. Okay. So if we recall the lawnmower example that we had earlier, we're going to apply just that. Again, you can pause or just follow along with the walkthrough here. So we have our buddy Joe here out mowing the lawn. And again, we already calculated that that's going to take 1,536 joules. Okay, we've done that previously. But how many kcals is that? How do we figure that out? Well, we use a conversion. Okay, we use that turn this this known conversion values and calculate that out. Okay, so if I set up my equation, I have my answer here. I know that I want joules, so I can cross eliminate on the bottom, right? And I know that if I have 4,184 joules, that equals 1 kcal. Okay. So 1 kcal. Okay. But when I look at this, I know gone with the joules units, left with kcals. And so when I divide 1,536 joules by 4,184, my value that I get is 0.367 kcals. And so if you look at packaging in Europe on food, it'll all be in it'll give it to you in kcals. So you, whereas here we use calories, right? So if I want to convert from kcals to calories, all I have to do is multiply by 3, and I can see that when I perform around 1,500 joules of work, I'm really utilizing about 367 calories of, I guess, food energy, we could think of it. Okay, cool. So we can figure out some fun stuff like that. The part B here is a bit conceptual. So again, the force, as we remembered from last time, equals 0 work. But just by standing there, so for part B, Joe, would we say that he's working? Well, yeah, Joe just standing there, his body is still creating and producing energy just to sustain living tissues, right? Now, is he doing work? Well, no. But is there work being produced in his body? Yes. So that's where it's really important to be clear. What is your system? What is your object that you're speaking about that's consuming or producing energy and or work, okay? So to kind of build on that point a little bit, if we look here at the total percentage of daily expenditure that each of us produce in our bodies, a lot of the chemical energy that we take in through food is purely used by our resting metabolic rate, which is our bodies at rest. Some of it is used for breaking down and taking in foods. So we actually have to expend energy to get energy. And then there's other parts about just moving around in our day. So daily exercises is the pink color here, and that would be like getting up and I was going to say walking to your fridge. So walking around, getting from your car to the building. If you take the bus, or SkyTrain, making sure you get to those stations. That's that kind of non-exercise. And again, exercise is specifically physical activity dedicated with and specified for the purpose of expending energy, essentially. So performing some sort of a sport or working out. Okay, and that's such a very small, up to, and this is a bit of a higher estimate, 10% of your day. That would be a very long, quite strenuous maybe hour and a half workout. Okay, so again, when we're looking to help clients or ourselves expend energy in an efficient way that might help them lose or manage weight, you're really looking at various ways to increase resting metabolic rate as best you can, and ensuring that at the very least, some percentage of this 10% is being expended through exercise, okay? Right. And of course, just to be complete in the answer, yes, nutrition is a huge part as far as weight management, but I digress. We'll return to the metabolic expenditure aspects of things. So when, again, we're thinking about how is energy used by the body, we see that there's actually a small amount that's called non-conservative work. So we get our food energy in, and a lot of energy that our body produces is thermal. And arguably, that's wasted energy. Now, true, our body has to be a certain temperature in order to maintain all the processes that occur in it. So for example, enzymes need a very specific heat level for them to be able to stay in the proper shape and work. Okay, once they become deformed or change their shape, they no longer can produce work. And our body is a huge system of enzymes that are just set up to help all the chemical processes in our bodies. Okay, it's a major component of it. So thermal energy is huge. Some of that energy, yes, is stored as body fat. Again, very important at certain levels, and only a small percentage actually gets performed or transferred to external work on the environment. Okay, and so if we think back to watts and what we've learned about watts, right, is it's an indication of power or the rate at which work is performed over time. So if you look at the energy consumption of different activities, we can see sleeping, very minimal amount of watts expended. It's really like a resting level of watts is somewhere between 80 and 120. So essentially, even at rest or at sleep, you're a light bulb. Okay, most incandescent light bulbs anyways, and even some LEDs are about 80 to 120 watts. Okay, then we get into greater and greater activities. No, shivering is 425 watts, so you do that to produce heat when your body temperature gets too cold. So your body's like, hey, processes are shutting down, enzymes can't work as well in our body anymore. We actually have to purposely expend heat, typically stored fat, through a type of fat called brown fat that creates thermal energy for us. It metabolizes it and creates heat. So that's shivering. So more than walking and even cycling slowly, all the way up to, if we look at running cross country or even more so sprinting, we see that there's a huge amount of watts expended during that, okay? And a large component of that energy consumption, again, is heat, okay? So with all this heat loss, we can determine and state that as far as our energy use as biological systems compared to other mechanical systems is actually quite poor, okay? Why am I saying that? Well, the work or energy that we put out relative to the total amount input into the system. So if I, it's like a score on an exam or a quiz, right? So you want the higher the mark or the number on top, the higher percentage or the higher efficiency or return on the input that we get out, okay? So what do I mean by all of this? Well, for the amount of energy that we put into, say, a gasoline car, we only get back 30% of what's actually expended. Where does all that energy go? Well, if you think about it, internal combustion engines or ICE engines are small, repeated explosions. Well, what happens in an explosion? A lot of heat is given off. So 70% roughly, and there's other things like friction and stuff, but roughly, to ballpark, about 70% you could say is potentially lost through heat. So when you compare that to an electric motor, significant difference. So it is much, much more efficient to have an electric motor trying to move mechanical parts like your drivetrain on your vehicle than it is a gas engine. Okay, it's just another crucial reason why converting to either EV or electric vehicles or potentially even hydrogen vehicles is just so crucial at this point in time for us. 70% of the gas that you put into your vehicle is just lost through the engine block through heat and other components of the engine. Wild, absolutely mind-boggling. Could you imagine, just picture that every time you're paying for gas at the pump, 70% of that is just heat expended by your engine, not moving you anywhere. Yeah, so transit is great. Lots of options there for you. But I digress. The point that I want to compare that to is us and our interaction with machines. For example, like a bicycle is about 20% efficient. So us in and of ourselves, we're actually very close to a gasoline engine. We lose a huge amount through heat when we're resting. Sorry, I forgot. Maybe I don't have the slide here anymore. But so about 25%, 20 to 25%. So when we do something like are on a bike is actually one of the most efficient ways that we can move ourselves around. It's actually quite profound. But that being said, if we look at something like swimming along the surface of water, we notice that our efficiency drops down to 2. Okay, why is that? Well, we spoke about this the other day when we were talking about drag, right? Drag is a force. So out of the work that we're trying to get in, moving us in a certain direction, a lot of it is lost through heat and heat through the water. So we lose a lot of energy that way. But a lot of our efficiency as well is held back through drag and other frictional forces, okay? So something to keep in mind about efficiency there. It's just kind of profound. All right. So with that wraps up our discussion on energy, work, and power. And we found a few new ways and cool means of calculating some fun variables. Okay. Here's your learning objectives to help you study for the final. And we'll catch you next time.